All right. Hello, everybody. Come on in. Sorry about it taking me so long to get here. Like I said, I got caught in a lot of bad weather on the Virginia Beach side. Then when I got to North Carolina, it hasn't even rained here yet. Not even our driveway's wet. So, anybody have any questions before we get started? Anything confusing you or anything?
What is the non-partially filled capacitor assignment?
Oh, that's one I made up. Basically, I haven't assigned that to you yet, but so you don't need to do it. But if it doesn't have a good description there, don't worry about it. I'll make up a description. If it's something you want to do, then it's basically just like the next to the last example in chapter 24, or maybe the last one, where they basically have a capacitor that has a dielectric in it, but the dielectric is only 1 millimeter thick, and the gap between the two plates and the capacitor is 2 millimeters. So you imagine centering them up. It's the last example I worked, I think, in the last lecture. So it's something like that. Probably what I remember. I didn't even know it was available to you guys. But if it's what I'm thinking it is, it's one of the problems from the back of the book where they not in the back of the book, but from the end of the chapter. Let me see if I can find it real quick while I'm here, and I'll just tell you what the number is. Nope, not that one. But in the wrong chapter. That's unhelpful. Looking in the correct chapter. So definition of capacitance, parallel and series. No, not that. Energy, electric storage. That's a little bit much more than I thought. That's not it. That's not it. I don't see it there either. Huh. Here's some. I think it's number 64. That's an example. So 64 is very much like what I intended. Whatever that was, it was something like 64 in chapter 24. And you can look at 58 and 59. Those are both similar type problems, but those are ones where it fills, but you have different dielectrics in different parts. So those are a little more complicated, but easier, whereas the 64 is equally complicated, but probably a little bit harder. And you can try that. So anything else? Anybody have another question?
Is this lecture going to go all the way through the normal time?
Uh, it might not. Normally, what I'd probably do is try to run it for about an hour and then take a break and come back at 5:30. That would be my ideal scenario, but it depends on how quickly we can work and that sort of thing. But you're free to go at any time. You're not really required to be here until 5:30. I just wanted to give you all the option in case you had real-time questions. I think a synchronous meeting on Zoom is infinitely better than watching just a video. So that's why I wanted to give you all the option if possible. You guys ready to start up then? All right, so what we're going into is chapter 25. We've finished chapter 24. I've adjusted the homeworks. I think I might have even adjusted the homeworks for chapter 25, but I'm going to check them again after either this or after class tonight. But basically, chapter 25 is on electric current and resistance. And we start off with basically the idea that Luigi, who's the good brother of Mario, of course. No, not really. That's from a Nintendo thing. But yeah, Luigi Galvani is the person to have invented the battery. And basically, what he found out was that when you put dissimilar metals in an electrolytic solution, those dissimilar metals can actually produce, once they're touching, they can produce a potential difference between the outer plate of one and the outer plate of the other. So, what I've told my students on many occasions, and actually made for students and other people that come to see me in various science shows, you can imagine, pretend this is like a prescription bottle. if you took a prescription bottle, those little, orangish, yellowish looking bottles that you get, what you can imagine doing is going getting a zinc washer or a zinc disc from a Home Depot or Lowe's or something like that, and imagine connecting a wire to it. Maybe you solder it to the surface of the zinc disc, or maybe you just wrap it around the metal part from that. And then what you're going to do is you're going to take your prescription bottle and you're going to fill it up with an electrolytic solution. What does that mean? A dilute acid or a dilute base would work. So you could take some, soapy water, for instance, that's likely going to do it. Maybe not exactly soap. Maybe you want to use something that, for instance, has some sodium hydroxide in it or something like that. Or you could take lemon juice, or you could take vinegar, or you could take watered down vinegar. That would be even better. And various other liquids. In principle, if your water is not clean enough, and as long as you don't distill it, then water would in principle do. It just has to have enough free ions to exchange stuff chemically. So just imagine filling that prescription bottle up to some extent, maybe about a third or half of the way full. And then you're going to take that zinc washer that you have a wire attached to, and you're going to put the side that the wire is attached to on the bottom, and you're going to lower the zinc washer into here. Now, what I personally do, and I don't think you necessarily have to, is I like to put a little piece of gauze on top of that zinc washer, and then put a penny on top of that. That penny is not copper. It's coated in copper. It's got a copper plating. It's probably, well, I forgot. I think I looked up that metal before. It's not a very expensive metal inside, but the main thing is it has a copper outside. And then you could drop that in the solution. And if you took another wire and attached it to that penny, what you'd find is there'd be a voltage difference between those two wires, the wire touching the zinc and the wire touching the copper. And that voltage might be on the order of 0.15 volts or 0.2 volts, something like that. But the neat thing is, let's pull that wire back off the penny, put a gauze on top of it, put a zinc washer again, put another gauze, put another penny. Now that it's twice as many parts of dissimilar metals, if it was 0.2 before, now the voltage is going to be like 0.4. Put another gauze on there, another zinc washer, another gauze, another copper penny. Now you're going to get like 0.6, and keep on doing that. You can stack it up as many times as you want, and eventually you'll start to run out of number of times you can double it, such that it automatically makes the last one go up by 0.2. It might actually start to level off a little bit, and you're basically running into the limits of what you can do with that solution, that stuff of that sort. But anyways, it does work, and it can run stuff. So for instance, I would normally take that and then connect it, for instance, to a light emitting diode. And once the light emitting diode had a voltage of about 0.4 volts, that's usually the turn on voltage, then the light would turn on and that would work fine. If I tried to connect that to an incandescent bulb, to an incandescent bulb like the light bulb you did in your lab, it would take quite a bit more to do it. You probably might have to get, a stack of 40 pairs of zinc and penny dissimilar metals. That might drive enough electric potential and therefore enough current through the light bulb to get it to begin to light. But it'd be very hard. So really, I normally do this kind of demonstration with a light emitting diode, which takes a lot less voltage. Now, another thing you could do is you can also just take and buy a lemon or an apple or a orange or a pear, a tomato, a banana, and buy you like some number 10 or even like number 01 or number 1 wire made out of copper with no housing on it, and just jab it in one side of the fruit, vegetable, or whatever you bought was. And on the other side, just take a galvanized nail and stab it into the fruit, vegetable, or whatever it is. And that'll show a voltage difference between the nail and the copper wire. That should probably be on the order of 0.1 or 0.2. So you can then stack those up where you take another, let's say, lemon, and this time you connect the copper wire that's in the first lemon to the galvanized nail in the second lemon, and you take and measure the whole voltage from the first copper, from the second copper wire to the first galvanized nail, And if that was 0.2 before, two of them should make 0.4. And you can keep on doing that by setting them in series. And that's what we normally do is we can take a typical AA, AAA battery, which is nominally supposed to be 1.5 volts. When you first open it, you're probably going to find it somewhere between 1.68 and 1.72 volts. But if you stack them on top of each other, where the negative side of the, say, the AA battery is at the bottom, and then the little nipple that sticks up, that's the positive side, that's up here. Now you take a negative side of another AA battery, stick that on top, and then if you can measure the voltage from the nipple on top of that second battery to the negative on here, you're going to get basically something like 2 times 1.5 volts. Well, if you're not drawing a current, you're going to get more like something like, and they're brand new, you'll get more like something like 2 times 1.72 volts or 2 times 1.68 volts. So you can keep doing that as well. And that's the way we normally do it. If you see an electronic device that takes multiple batteries, almost always it's going to be wired such a way that the negative on one wire is the negative for the whole battery bank, or excuse me, the negative for one battery is the negative for the whole battery bank. And then the last battery that you put in there, that positive will be the positive terminal for the battery bank. And what you have is the positive terminal of the first battery touching the negative terminal of the second battery, and the positive terminal of the second battery touching the negative terminal of the third battery, and so on and so forth. Sometimes they'll just let them stack up like that. Sometimes they'll stack two, and then there'll be a little piece of metal that connects the positive terminal of the two to the negative terminal of the next two. And you can do it like that as well. In fact, that's one of the things that Apple did. He really, Steve Jobs loved aesthetically pleasing things. So he didn't like having basically, batteries that were stacked on top of each other or stuff like that. He actually just put them side by side and just ran the wire around so it would look a little nicer. That's kind of neat. I can see the aesthetic appeal to it, but really at the end of the day, I like stuff as a teacher that makes obvious what you're doing. So when you stack negative, positive, negative to positive, negative to positive like that, you're building up a bank of series batteries, and the voltages add up to give the total voltage. You can, in principle, put batteries in parallel, and this chapter talks about it, but I'm going to pretty much skip that section altogether, not out of skipping it because you're not responsible for it, but skipping it because I think those examples are pretty straightforward compared to the examples that I plan on working in this as well as in the next meeting, which is today at 5:30. Okay, so far as this chapter 25 goes, it has a section on power and household circuits. That section is completely relevant. I would say all of these sections you should really read, but section 25.9 on superconductivity, section 25.10 on electrical conduction and the human nervous system, even the problems in there are optional. So in other words, I wouldn't be upset if the homework set had some problems from superconductivity or section 25.10, but I'm definitely not putting any of those on the homework, on the actual tests. So don't worry about that. So 25.9 and 25.10 you can skip. Let's go ahead and get started. I've given you the explanation of how to make a battery, and you can see the diagram that your textbook has. That's actually the diagram that Luigi Volta submitted for publication when he invented it. And if I remember correctly, it'll have the little links, little pieces of metal, and the metal, one of them will be marked A and the other one will be marked Z. The Z is zinc and the A is silver. And what he discovered was that for a zinc silver contact, the voltage jump across that was about 0.7 volts. Today, we actually determined that that's about 0.78 volts. So it's actually a little higher than what he reached. But you can see in that particular example from figure 25.2 that he actually has a bank of 16 of them stacked on top of each other. So in principle, he might have 16 times 0.7 volts for that whole bank. And you can, of course, keep adding them up and stuff. There will be a point at which the returns aren't as great as they were in the beginning, but in general, you can still get them to do quite well. Far as figuring out what metals work best, that's a matter of figuring out the electronegativity, which you might recall from chemistry is something that was done a long time ago. And it's basically trying to figure out, hey, in a battle for an electron, what element beats what element? So you could take, for instance, and say, let's do hydrogen. So you're going to imagine some way in which you're going to make hydrogen into a solid. Obviously, that's a problem. So you might want to skip ahead to not hydrogen and not helium. Maybe you could take lithium, though. And then you take lithium and say, let's let's rub lithium up against beryllium, okay, and see which one is likely to become a little more negatively charged and which one's likely to become a little more positively charged. The one that's more negatively charged has a greater affinity for electrons, and that's how it's going to behave. The other one, on the other hand, compared to lithium, for instance, and beryllium, depending on which one was the first case, that one's going to actually be one that's more likely to give up the electron. So at least with lithium, maybe you'd conclude that lithium will steal an electron, and beryllium's too weak to fight it, so beryllium will lose an electron. But you can do that pairwise for all the various elements, and you can even start using compounds and things of that sort. And eventually what you'll have is a table that lists the strengths of the electron affinity for each of the atoms that you're using, or each of the molecules you're using. And then from there on out, you can predict a priori, if you put two metals together, which metal is going to be the positive terminal and which metal is going to be the negative terminal. It turns out, by the way, that you don't have to just use metal. Carbon works quite well, and that's usually the number one thing that's used in a lot of modern day batteries. So the way a modern day battery would be created is they take and make like a little cup, let's say a C battery. So imagine the size of a C battery, or a D battery, imagine the size of that, or a double A or a triple A, just imagine the size of that, and then make a cup that's as tall as the battery is tall and exactly the same diameter as the battery. Make that cup out of zinc. Okay. So zinc will be one of the metals you're using. And then what you're going to do is you're going to take a carbon rod and stick it right through the middle of that little cup that you made out of zinc, because it's going to be open on top. So you stick that in there and fix it some way that it doesn't move around. Now what you're going to do is put, instead of an electrolyte liquid, you're going to put an electrolytic paste. So you can imagine taking sodium hydroxide if you want an alkaline battery, or you can take sulfuric acid if you want an acidic battery. And you can sort of dilute them and actually put things with them to make them kind of pasty as opposed to a liquid. It doesn't matter too much. There obviously are some good chemicals to use and some bad chemicals to use. And I'm not a person that makes batteries for a living, so I don't know exactly what to use. But all I know is, as long as I've got a free source of ions in the electrolytic paste, it'll work well. So what we're going to do now is take that zinc cup with that carbon rod going down through the middle, and the carbon rod is going to be taller than the zinc cup. It's going to be about as tall as from the bottom of the battery to the top of the nipple of a battery. And now you're going to fill in all the space between the walls of the zinc cup and the carbon rod. You're going to fill that up with the electrolytic paste, leaving a gap even between the bottom of the copper rod, the bottom of the carbon rod and the bottom of the zinc cup. Then you're going to put some kind of insulator on top so that you can separate the zinc from whatever metal you put on top of this contraption. So we'll put some kind of insulator to insulate the zinc cup below from the metal that I'm getting ready to cap it off with. Then I put that metal on top. Maybe it's steel, maybe it's tin, I don't know, maybe it's aluminum. Doesn't really matter too terribly much. But that metal is going to act like the lid to keep that electrolytic paste from popping out. And it's going to have a little nipple on it in which the carbon rod just fits. So basically, you're taking and making that cap, which might be made out of aluminum or something, you're making that the terminal for the carbon rod. That carbon rod, because carbon has a typicalness, or has a tendency to lose the electron, that carbon rod is going to be the positive terminal, which we call the anode, and the zinc cup is going to be the negative terminal, which we call the cathode. And then you seal them up with some kind of wrapper or sticker or something like that, just to make sure that it's actually watertight. I do not recommend busting open one, though I have done it in the past on multiple occasions. I've since learned that it's not the safest thing to do, and there can be some negative repercussions to doing it. But luckily, that all happened, and I did all that kind of stuff when I was younger before I had influences of people that knew better. So I survived. All right. So that's a way you can make a battery. And it turns out that really, like if you look at batteries, I have a stair climber over here. Actually, it's an elliptical trainer over here. And it's got a really big battery. Like the battery's this long, it's about that wide, and it's about that tall. Well, about that tall. And it's kind of, looks like a very odd battery. Well, it went bad, and I took it up to Batteries Plus, and they opened it up and they showed me something. And it was amazing. It was just a bunch of D batteries inside of there. That's pretty much how they make batteries. Is they just maybe they make double A's, and if you're wanting something small, you put a bunch of double A's in series so you can get up to 12 volts. So a double A being 1.5. If you take two of them, that makes three. If you take four of them, that makes six. If you take eight of them, that makes 12. You can put them together in some way and then seal them up and put a fancy label on it. And it looks like you just created a 12-volt battery. Nah, you just took a bunch of double A's and made it into a 12-volt battery. And that's what a lot of times I discover, for instance, the removable battery on a power driver or a drill will be. Okay. Any questions on that? All right, so that's the concepts behind it. And I would have just skipped it because really I'm trying to just solve the problems that are here to make sure you can understand the problems that I think are important within chapter 25. But I think that needs a little bit of description. They have various pictures, for instance, of batteries in section 25.1, 25.2, and so on and so forth. They tell you how to connect batteries to light bulbs. They show you how the light bulb's actually made. I'm pretty sure your lab instructor did the same thing when y'all covered the light bulb. But just in case, if you were to look at a light bulb, it normally has a threaded part down at the bottom. And then if you look at the bottom of that light bulb, you'll see the gold threads, and then there will be something shiny and black inside the gold threads, like looking at it from the bottom. And then in the middle of that shiny black circle, which looks like a donut now because there's something in the hole, is something that looks like a dull, ruddy sort of look. Well, not ruddy, but a dull looking metal. That metal is usually lead because it's meant to be able to be soldered. So what's going on there is that shiny black stuff is an insulator that protects the electrode that comes through the lead from touching the electrode that is the threads of the light bulb. Then a wire just runs from that little lead terminal at the bottom in the middle of the insulator, runs up, and then maybe does some little swirlies, and then comes back and then attaches to the threads, so that when you actually plug it in, one terminal plugs into the bottom. That allows, you can pretend it's conventional current, that allows positive particles to roll up through the wire and then go through that little curly part and then come back down and exit through the threads. And in fact, the direction you go doesn't matter. So you could go in the threads and out the hole in the bottom, or you could go in the hole in the bottom and out the threads, doesn't matter. That's an incandescent light bulb. That wire is often made of tungsten or something along those lines that is somewhat of a conductor, but it's also quite resistive. And it also has a resistance that is what we call non-ohmic. As you saw when you plotted voltage versus current for a light bulb, in principle, it should have looked something like this. If you stopped it a bunch of times and turned the voltage back, it won't look this good. But in general, it should look like a slowly ramping up slope, and then it curves like that. What's going on there is, for a low current, you have a low resistance and the temperature hasn't gotten very high, so it stays low. So you have a little line like this. And then you go a little bit more current and it's still a little bit more line, but it's getting a little hotter because the current's going up. So the slope, which turns out to be the measure of the resistance, goes up as well. If you go a little further, it goes up a little more, a little more, a little more, a little more, like that. That's how the light bulb responds. If you actually get it high enough, to a high enough current that it actually reaches a temperature of around 2700 Kelvin, then the tungsten actually glows in the visible light. If you go even higher, it starts to turn less red looking and will actually become sort of white light. And really what that is not so much white light as is all the colors of the rainbow, but all of them with so much intensity that they're sort of combining to form white light. weird thing when we mix a bunch of colors of paint together, we get something called mud that looks, sort of brown or sort of gray or sort of black or something like that. When you mix all the colors of light, though, you get white. So it's really quite backwards when you talk about the mixing of light versus the mixing of paint. So that's what we cover in chapter 25 regarding section 25.1, the electric battery. And what I will tell you is that in general, the electric battery is modeled as if it's a ideal battery, what we call an EMF. So we use this script E, this fancy E, which you'll see in the next chapter. We use that for EMF, which is electro, ELECTRO, motive, MOTIVE, force, FORCE. It's not really a force, but that was a phrasing that we came up with, our scientists came up with well before we knew things like voltage and current and stuff like that necessarily. So we start off as electromotive force. So if you had a 12-volt battery, what I'm saying is we might model that as a pure 12-volt electromotive force, but then still within the battery, the wire would leave the positive terminal, say, it doesn't matter which side, but I'm pretending that like we're going to put it after the positive terminal, and we go into a little internal resistance that might be 0.3 ohms or half an ohm or maybe even a whole ohm. That resistor over time, we model it as if the battery is that ideal EMF plus a small internal resistance on the order of 0.5 ohms. And that's what we model the battery as. But over time, what happens is the particle that's actually able to steal, or excuse me, the rod or the terminal of the battery that's actually able to steal the electrons, that will collect electrons, and the atoms, the positive atoms that came out, they'll actually fall off, and slowly you'll lose that metal that's got positive ions falling off into the water solution. And as that happens, you have less ability to create the voltage that you had. So that, AA battery that when you first opened was 1.72 volts, it'll start to go to 1.71, 1.70, 1.69, 1.68. And eventually it'll get down to being even less than 1.5, which is the design spec. So when someone tells you, or a manufacturer sells you a product and says you need 2 AA batteries or 3 AA batteries, they're expecting those to be 1.5 volts, and they'll stay at 1.5 volts for a while. But the way we model it is as that time goes by, that internal resistance gets bigger and bigger. So it moves from, maybe a 0.3 ohms to ultimately a 1 or 1.5 ohm. And that also covers the fact that by doing that, once you actually apply a load to it, you're going to get a current going out of the positive terminal, going through the internal resistance, leaving the positive terminal of the battery, going through your load, coming back into the negative terminal of the battery, and so on and so forth. That, if you then take a connection between the positive terminal of the battery and the negative terminal of the battery, you'll get a voltage that even when it's brand new, remember before we put a load on it, it was like 1.72. When I put a load on it, that might drop down to more like 1.58 or something. Okay. And that internal resistance is the reason you're seeing it, because obviously Ohm's law says V equals IR. If we have a resistance of 0.5 or 1 ohm, but we have a current going through it, then you multiply that current times the 0.5 or the 1 ohm, and that's the voltage drop across that resistor. So if you're coming from the negative terminal of the battery, you go from the negative terminal to the negative terminal of the ideal EMF source of 12 volts. Then you jump to the positive side of the ideal EMF source. So at that point, when we were on the terminal end, the voltage was 0. But when we're on the positive side of the EMF force, the voltage is now, say, 1.5 or 1.72, or if we're talking about a 12-volt battery, we'll say it's just 12. But we just calculated V equals IR for the internal resistance. So after you leave the positive terminal of the ideal EMF source, the voltage is going to stay essentially 12 volts, 12 volts, 12 volts, because the wire has almost no resistance compared to the resistances in the circuit. But it's going to hit that internal resistance, and you can picture that now as dropping from 12 to, let's say, 11.9 or something. Okay. So that's how we model it. That'll come in handy as well at a later time. And I think that's a pretty good and exhaustive discussion of batteries. Your book does talk about electric cars. Again, I highly recommend you guys reading that. I actually recommend you reading the entire book. That's what makes you, at the end of the day, once you've forgotten how to solve all those physics problems, just because you haven't been doing it every day, and once you've forgotten all the minutia about how to conduct a path integral and a surface integral and all that stuff, what you're left with is a string of coherent facts, if you will, that you sort of build a model around, that you can think about the universe and how it works. And that's where that comes from. That knowledge is coming from the reading of the text. So do read that. After section 25.1-2 on electric cars, we go on to electric current. And that's where I'm going to start now. So does anybody have any questions on that battery discussion, the internal resistance, all that good stuff?
So, so you said the negative electrode is the cathode, and then the positive electrode is the anode.
Yes.
Like I looked it up on Google or something, and it's like the opposite.
That there's a real possibility. That's why I'm hoping I'm right, because I happen to remember just covering that yesterday. But I literally look it up just about every time. I will double check again just to make sure. But generally speaking, the one terminal is going to be negative, the other one's going to be positive. The negative terminal, I'm looking in your book right now just to double check my work. Section, let's see.
Yeah, I think the book says cathode is the negative.
Yeah, the positive electrode is called the anode, and the negative one, the cathode. So for in the case of, I'm looking, for instance, at figure 25.3 in the book, that's got a little glass of sulfuric acid, probably diluted, in which is a rod of carbon, and that rod is being called the positive terminal. So that would be the anode. And the zinc electrode is called the negative terminal, and that would be the cathode. And what that's supposed to mean, the acid tends to dissolve the zinc electrode. Each zinc atom leaves 2 electrons behind on the electrode. Okay, so what we're saying is the zinc was the one that lost the actual atom, but it left the electrons behind. And that's the reasoning that we use that to call it the cathode, because it's the negative electrode. So I'm not sure what aspect you saw on Wikipedia. The good news is I'm not ever going to ask you which one's the cathode and which is the anode, because I've forgotten that so many times in my life. It's just easier to look up when I need it. But what I will tell you is that the one thing I've always relied on, though sometimes I go a long period of time without thinking about it, so I forget, but I remembered hearing about cathode ray tubes, and we've seen cathode ray tubes, especially if you've used that little well, one of the devices we have in our lab is this big glass, looks like a bulb. It's a big glass clear bulb, and inside's got a little target. And we put a high enough voltage on there, and you get a little blue beam of electrons on there. That blue beam of electrons is what we called cathode rays. And in principle, negative charges should be running from a cathode. So you can say, oh yeah, that's electrons, because the cathode was negative. So hopefully that'll help you, but under no circumstances will I be asking you that question. Okay. So sorry about that. And also I feel you, because that's exactly the same problem I've had in my entire life. All right. So what I wanted to show you about this is we already talked about batteries. So I'm going to go ahead and give you this, even though you've probably seen it already. Basically, the symbol we use for a battery is a short line and a long line. And the short line is understood to be the negative terminal, and the long line is understood to be the positive terminal. But we don't have to mark them plus or minus. In fact, we can just do this, and that's still a battery. But remember, it always set up that way. So if you are trying to find out voltage drops and gains across different parts of a circuit, if you go from the short leg of the battery to the long leg, that's a voltage increase. If you go from the long leg to the short leg, that's a voltage decrease. That's something important to know. So that's how we draw batteries like that. Now, an example of a circuit, for instance, would be a battery right here. And then we could go on, and then we just say, here's a magical thing called a load. And then out of that goes a wire to return the actual charges. So we work with conventional current, which goes on the assumption that we're pretending positive particles exist, such that when I connect this battery to this wire, the wire being a conductor and the battery having a positive charge terminal, that positively charged terminal is going to compel positive charges to run away from the positive terminal of the battery along the wire. And you can't have a complete circuit that works unless that positive terminal, which is compelling positive charges to run away from it, has a path to have those positive charges to return through the negative terminal. If you don't have that return path, it's not a real circuit, and it's not going to work. So that'll help you when you do conceptual questions about, what's the correct way to connect a battery to a light bulb. You'll see that's one of the ones in your textbook. Okay. Now, this load can be just taken as a resistor, which you probably remember, that's the symbol for a resistor. So there I've made it a little bit more normal. What we do though is we think of current as the amount of charge flowing through a particular point in a circuit in a given time. So you could say on average, the current would be the amount of charge delta Q going by a particular place in the circuit divided by the time taken, which is delta T. Now, from 241 that the generalization of this is that the instantaneous current, i.e. the current at any point in time, is dq over dt. So that's a form we're going to use, and that's a form that we can make a differential equation out of later, for instance, when we go to discuss, for instance, a capacitive resistive circuit. So if you had a circuit with a capacitance and a resistance in it, there's a differential equation that tells you how it behaves. And the I part of the differential, or the I of the circuit, is the part that becomes a dq dt. So that might help you as well. So as an example, just with this, we can think of basically let's say a steady current. So this is going to be my example. I'll call that example 1. A steady current of 3.50 amps exists in a wire for 7.00 minutes. A, how much charge passes a given point? I shouldn't say given, maybe I should just say a particular point, because I'm not going to spell out a specific point for you. Passes a particular point during that time. And in part B, since we actually know that the conventional current that I've been telling you about is not really true, there's not really positive charges running around the circuit. In fact, there's actually negative charges, i.e. electrons, running the opposite direction around the circuit. So how many electrons is that? Okay. So our solution is we're going to employ I on average is equal to delta Q over delta T. Therefore, delta Q is equal to I times delta T. So for part A, I'm going to say delta Q is equal to 3.50 amps. Now, what I need you to understand is since I is equal to dq dt by units, that means I is equal to delta Q over delta T. And the units of Q, of course, are coulombs, and the units of time are seconds. And what we do is we define 1 coulomb per second to be 1 amp. So instead of writing an amp here, I'm going to write 3.50 coulombs per second for the I, and then I'm going to say 7.00 minutes. But you can see that minute doesn't cancel out with the seconds. So I've got to now say, okay, well, 1 minute in the bottom can cancel out with the minute in the 7, but on top we have to have this fraction be 1, so I'm going to say that's 60 seconds, like that. So now I have, instead of minutes, I have seconds, and then the seconds multiplied by the seconds in the bottom gives me an actual coulomb. So the ultimate answer is 7 times 60, which of course is 420. And then you're going to multiply that by 3.50, and that gives me 1,470. So that's 1,470 coulombs that are passing by in a given amount of in the 7 minutes that they asked about. Anybody have any questions on that? Now, that might not sound like a lot, but you'll see there's an example in this chapter of the book where they give you some real data, commonly known data anyways, of roughly some of the parameters of a lightning bolt. And in that, I think that lightning bolt turns out to be delivering like 100 coulombs. So even something as powerful as a lightning bolt might not deliver more than, say, 20 or 100 coulombs. So 1,470 coulombs is a buttload. Not only that, that lightning bolt, when you look at the example, it actually is a power source of 5 gigawatts. And just to give you some idea, a gigawatt is 10 to the 9th watts, but that's roughly what a power station would actually put out. So for instance, if you build a steam powered if you build a steam powered turbine to generate electricity for a plant, it's not unusual to have that plant be supplying, 10 gigawatts or 100 gigawatts or something like that. So a gigawatt's a pretty good size amount of power. All right. Anybody have any questions on that part? Because now I'm going to do part B. Part B says, how many electrons is that? So I'm going to say the number of electrons, which is E minuses, I'm going to say is equal to delta Q, which will be in coulombs. And then I'm going to divide that by E, which is, actually, I'm going to divide it by the absolute value of negative E. So I'll do it like this, because negative E is the number of coulombs per electron. Okay. So the delta Q is 1,470 coulombs. The E is negative 1.602 times 10 to the negative 19th coulombs. But as I said, I am going to do the absolute value because I really just care about the number of electrons. I don't care about that they're negative or anything. So I'm going to say 1,470 divided by 1.602 e to the negative 19. And that gives me 9.176 meaning 1 extra sig fig, 9.176 times 10 to the 21 electrons. So the way I'd really prefer to write this when I'm doing this type of calculation is I'd call that coulombs per E minus. And then when you divide coulombs by coulombs per E minus, then the answer comes out in E minuses. So that's kind of nice. But that's the number of electrons. Anybody have any questions on that one? So that's supposed to be really, really straightforward, easy kind of stuff to do. Your book talks about how to connect batteries. Again, I'll leave you to mess with that. I will tell you, have any of you ever heard of amp hours? Have you seen it, like, for instance, in the checkout line at Walmart, or have you seen it on some electronic device that you bought recently? Anybody seen amp hours before? So, example 2, what is an amp hour? Okay, so what an amp hour is literally an amp times an hour. Okay, so if you look at an amp hour, 1 amp hour means 1.000 to any number of decimal places, coulomb per second. So that's the amp part, times 1 hour. But of course, 1 hour is equal to 3,600 seconds. So now you can see that I'm going to get 3,600 coulombs for 1 amp hour. So the answer is the amp hour is a unit of charge, and it is 3,600 coulombs. So, for instance, the item I was trying to get you to remember is, and you will see it in the checkout line at a Walmart, for instance, is those little portable chargers you can plug into your phone. They look like a phone basically, but they have, you know, USB ports out of them, and they're often 10,000 or 100,000 or 200,000 amp hours. So you can imagine that's literally 100,000. If you're talking about 100,000 amp hours, that's 100,000 times 360. So that's literally like what, 360 million amps or coulombs. You can do that and, you know, use that as a figure. It's not very helpful, but if you actually use a device that tells you exactly what current goes into your phone while it's being charged. I happen to have bought one from like Wish a long time ago. It's basically just a little USB port. It's got a little LCD screen on it, and then it's got 2 plugs that you plug into a wall. So I plug the plugs into a wall, and then I plug the USB end of my Apple Watch or my Apple phone cable into that. And it tells me, while I'm actually charging the battery, it tells me that I'm basically charging it at 5 volts, and that the amps is like 1.32 milliamps or something like that, if I remember correctly. But anyways, if you actually figured out what that amperage is and then use that to figure out how long it actually takes to charge your phone, then you could take the time that it takes you to charge your phone from 0% to 100%, convert that to seconds, and then multiply it by the amps, and that'll tell you essentially how much charge, quote unquote, charge it takes to charge up your phone. And then that also gives you an idea how good 100 amp hours or 100,000 amp hours is. Okay. Anybody have any questions on that? So that's just another unit we can run into. We're also going to define the kilowatt hour in a little bit. I'll tell you also that there's something called Ohm's law, which we've already had the lab now for that. You've had Ohm's law, you had series and parallel circuits. So I'm assuming you know the formulas for Ohm's law, and I'm assuming you know the formula, for instance, for the equivalent resistance in a circuit, that kind of thing. So let me recap those results real quick here. Ohm's law is this. It's V is equal to I times R. More generally, you can sort of pretend that V is directly proportional to I. That's another version of Ohm's law. Okay. And that's true. What it says is, hey, if I take an object and I put a voltage of 10 volts across it, then I'll get a certain current, let's say 1 amp. If I now take that same object and put, instead of 10 volts across it, I put 20 volts across it, then now I'm going to get 2 amps. And if I put 30 volts across it, I'm going to get 3 amps, so on and so forth. That's really what it says in that proportional form. In the equation form, what it says is there's a quantity that we call resistance, such that the thing that you have to multiply current by to get the voltage is the resistance. Now, we have, in that context, we have an idea where we say if something obeys Ohm's law, and what I mean by that is that thing obeys Ohm's law, at least within a certain range of values of voltage and current, i.e. certain powers, then that thing obeys Ohm's law. And every time you apply a voltage and a current, you get the same value R each time. That device would be called an ohmic device. So those little resistors that you use in labs, they're ohmic devices. Of course, they have limitations. If you put too much current through one of them, it'll sort of explode or burn up or melt or something like that. So they're not ohmic in the sense that it's always going to say the same R is 100 kilo ohms. It's ohmic in the sense that we have a very well-defined, basically amount of power that the resistance can do or can make, while it still remains a constant source of resistance. If you exceed that power, which most of the resistors you are using in your lab are like 1/4 of a watt, 0.25 watts. If you exceed that 0.25 watts, then the resistance is going to be quite different from there on out. Okay. Any questions on that? Now, the other formula I said I'm going to remind you of is that when you have resistors in series, the equivalent resistance for resistors in series is R1 plus R2 plus ... plus Rn for N resistors. So for instance, if you need a 10,000 ohm resistor and you only have 100 ohm resistors, you can just put a bunch of 100 ohm resistors in parallel until you've got enough that it adds up to give you 10,000. Okay. Also, for circuits in, or for resistors in parallel, we have an equation 1 over R equivalent sub P, which means parallel, is 1 over R1 plus 1 over R2 plus ... plus 1 over Rn. Now, this is a uniquely perverse sort of formula, although we see it's not that unique because I just derived the same formula for capacitors in series. But in this case, what happens is if you have a resistor 50 ohms and another resistor of 100 ohms and you put them in parallel, it turns out the equivalent resistance, meaning if you took those two legs out and just replaced it with a single resistance, that single resistance would need to be less than 50. In other words, the net resistance is smaller than the smallest one. Whereas in series, the net resistance is larger than the largest one. Okay. So keep that in mind. Those are the equations that I'm going on the assumption you already know. Your book does derive them, and I highly recommend you go through those derivations so you make some sense out of it. If you can, it's not that big a deal, but just keep plugging away and trying it, because you're ultimately learning how these things work, and that'll help. Now, with that V equals IR, ohmic devices would be things that you can plot V on the vertical axis and I on the horizontal axis, and for them, you would get straight lines. Those are all ohmic devices. There are, of course, things that aren't ohmic. So for instance, there's certain like Zener diodes that go like this and that. There are light bulbs that go like this and various other things. So there's a lot of things that aren't ohmic, but still in those cases, we say the resistance is variable over ranges of current and resistance, or excuse me, over current and voltage. And it's just a matter of checking the slope on the spec sheet to figure out what the resistance is at a given setting. So let's look at another example. I'm going to say example 3. A flashlight draws 500.0 milliamps from 2 1.50 volt batteries in series. A, what seems to be the resistance of the bulb? So that's A. And then B, what happens to the current when only 2.80 volts is applied? Okay. V equals IR is what we're working with. And of course, in part A, we're asking to find the resistance. So I can say R is equal to V over I, and that'll help me with part A. So R is equal to V. Notice I tried to pull some skullduggery or some trickery here by telling you it's a 1.5 volt battery, but there's 2 of them in series. Can anybody tell me what the voltage would be for that? Suspect someone might have typed it in to the chat. I was wrong. Okay. So yeah, if you stack 2 1.5 volt batteries on top of each other, they're going to turn out to be 3.0 volts. So I'm going to say R is equal to 3.00 volts divided by I, which is 500.0 times 10 to the negative third amps. So that's how I made the milli. So I'm going to say 3 divided by 5 times 500 times 10 to the negative third is going to give me 6.00 ohms. So hopefully you guys are all familiar with the unit of ohms from your labs, but that's what I get for that. Now in the second part, what they're asking for part B is, what if instead of us having a full 3.00 volts to put across the battery, across the light bulb, what happens if we put 2.80 volts there? And what we're going to do is we're going to go on the assumption, and from your lab this is not necessarily a very good assumption. We're going to go on the assumption that the resistance of the light bulb doesn't change significantly. So in this case, what I'm going to say is V equals IR implies I is equal to V over R. So in this case, I'm going to say 2.80 volts is the voltage, and I'm going to pretend that the resistance of the light bulb is going to be 6 ohms. So when I do 2.80 divided by 6, I get 0.4666. And that turns out to be amps, of course, which is 466.7 milliamps equals I. So that's our answer there. Anybody have any questions on that? All right, so that's the flashlight bulb resistance. What I'm going to do now is, by the way, your book does, just like your lab did, it tells you about resistors and how you can read the little stripes on the resistors to find out what the value of the resistance is, as well as the tolerance. So that's something I expect you to be able to do given the table, but I have to supply you with the table, so don't worry about that. Except for make sure you can do it like the examples in the book. So for instance, right here, I'm looking at a figure 2511. So figure 2511 has a resistor and this resistor, has stripes that are orange, orange, brown, red. So orange, orange, brown, and red. What is its resistance? So I'm looking in the table from the book. Table 25.1, I believe it's called. Actually, it's not even listed. It's resistor color code. Orange corresponds to, as a number, it corresponds to 3. Red as a number, or excuse me, brown as a number corresponds to 1. And then red as a tolerance, because this said orange, orange, red, brown, or excuse me, orange, orange, brown, red. That red must be a tolerance. When I look at red as a tolerance, then red is 2%. This is as number. This is as number. But the other thing is brown as a multiplier is 10 to the 1. So it's 10 to the 1 as a multiplier. And the way the resistor is supposed to work is this. Number, number, multiplier, and tolerance. So I had orange, orange, and then I had brown, and then I had red. So this resistance should be equal to orange, orange is 3, and then brown is times 10 to the 1. So we have 33 times 10 to the 1 ohms and 2% error. So that means R is equal to 330 ohms plus or minus 2.00%. 2% of 330 is 3.3. Actually, it's 6.6. Sorry about that. Is 6.6. So what this means is R is between 336.6 ohms. And then if I subtract 6, I might as well subtract 7. So that'd be 327. And then 0.4 omega. So it's 327.4 ohms up to 336.6 ohms. That's the way you do that. Your book also asks this other question, which I'm not listing this one as it, but there's something kind of important here. So you have this drawing, and then you have this, and it has a point B, and it has a point A, and it has a current I flowing this way. And what they ask for is, how is VA compared to VB? What about the current at A? So I'm going to write this as current at A. How's that compared to the current at B? Like that. Can anybody tell me, how is the voltage at A related to the voltage at B? Is there one larger than the other? Which one is it if that's the case? Are they equal? Anybody want to give me that? Ethan did get 3 earlier. Good job, Ethan. All right, I'm getting ready to let you guys go so we can have a break till 5:30. So what's going on here is current flows from high voltage to low voltage. Since the current's going to the right, we know VA must be greater than VB. So I'm going to put a greater than symbol here. Now, the other thing is conservation of charge dictates that if I've got a certain number of coulombs per second entering A, I don't see any extra paths between the A and B for those charges to go down. So everyone that goes through A has got to go through that resistor R, and it's got to go through that point B. So in this case, it's going to be equal. Okay, so that's just another conceptual question to make sure we're all on the same page. Let's go ahead and call a break now. I've given you about an hour of instruction. I'm going to start back up at 5:30, and we'll start right here because I'm going to go straight into this and then go into chapter 26, and hopefully I can do enough. If not, I'll put another video up later covering the other material. If I know when I'm going to be doing that, I'll let everybody know in case anybody shows up, but you don't have to. All right. See you guys. Thanks for coming. Anybody have any questions? You're welcome to ask before you split. All right. See you, folks.